Welcome to this explainer. Right now, whether they realize it or not, every single modern enterprise is effectively a data company. Think about it. If your application goes offline, if your analytical queries fail, or if your database just crawls to a halt, well, your business stops. The stakes are absolutely massive. And at the foundational level of ensuring you survive, there's one critical, overarching dilemma that every single engineering team has to face: build versus buy. Choosing between self-hosting your systems and fully committing to the cloud fundamentally shapes your infrastructure. It dictates your team's day-to-day operations, and it heavily, heavily impacts your bottom line. So over the next few minutes, we're going to unpack the hard realities of this choice. We aren't just looking at geographic server locations here, we're diving deep into the actual DNA of cloud-native architecture and the massive human shift in modern operations.
Let's kick things off by considering a really core question of business priorities. Should you build or should you buy? A highly effective rule of thumb in the tech industry is that anything constituting a core competency, like a true competitive advantage for your organization, well, that should be built and controlled entirely in-house. Everything else, the routine stuff, the foundational plumbing, that should typically be left to a dedicated vendor. Think about the device you're using right now. The vast majority of tech companies don't fabricate their own CPUs from scratch out of raw silicon. Why? Because the idea is kind of absurd. Companies like Intel or AMD spend literally tens of billions of dollars perfecting that fabrication. Buying from them is just vastly more efficient than trying to build your own factory. And when you're dealing with software and massive data systems, you have to make that exact same ruthless calculation. You have to decide who builds the software and, crucially, who actually deploys and operates it day in and day out. When you're navigating this choice, there is a massive spectrum of deployment options. On the far left side, you've got bespoke, entirely in-house software running on physical, bare metal hardware. Now, this requires the greatest financial and human investment, but it gives you absolute unyielding control over every single byte and process. Then, on the complete opposite extreme, the far right, you have fully outsourced, off-the-shelf cloud services or software as a service. Here, you surrender almost all of that low-level control, but you completely eliminate the headache of managing the underlying hardware. The reality, though, most companies operate somewhere in the middle ground. They use hybrid approaches. They might run off-the-shelf software, like a traditional MySQL database, but choose to self-host it on a rented virtual machine in the cloud, using infrastructure as a service. The fundamental law of this spectrum is pretty simple. Every single step you take toward fully managed cloud services reduces your direct control, but it profoundly shifts the operational burden away from your internal engineering teams. So here is our roadmap for today. We'll be looking at 1. The cloud trade-offs. 2. Cloud-native architecture. 3. Separating storage and compute. 4. Operations in the cloud era. And finally, 5. Making your choice. All right, let's jump right into part 1, the cloud trade-offs, agility versus control. We really have to objectively balance the amazing agility of cloud infrastructure against some very severe systemic risks. Let's look at the pros first. Cloud services offer unbelievable elasticity. You can literally spin up thousands of servers in seconds to meet a crazy traffic spike. And you get to completely delegate those exhausting, mundane tasks of basic system administration, like swapping out dead hard drives, straight to the vendor. But the cons are equally significant. The biggest downside? A total, undeniable loss of control. If a cloud service lacks a specific feature you need, you can't just build it. You just have to politely submit a support ticket and wait. Then there's opaque debugging. Imagine trying to figure out why your car is making a rattling noise, but the manufacturer has actually welded the hood shut so you can't see the engine. That's exactly what debugging a managed cloud service often feels like. You simply can't access the server logs or the raw operating system metrics. You also face the threat of vendor lock-in, where proprietary APIs tie your code to just one provider. And finally, there's the geopolitical reality. If your cloud provider is based in another country and international political conflict kicks off, you risk being completely locked out of your own data due to sudden sanctions. Yikes. Understanding how your specific workload dictates your infrastructure cost is absolutely critical. A lot of people just assume the cloud is automatically cheaper. Well, spoiler alert, it's not. It depends entirely on your load profile and the makeup of your team. If your engineering team already has deep physical deployment expertise and your server load is highly predictable, say a nice steady stream of traffic day and night, buying your own physical machines and running them is often significantly cheaper over a multi-year time frame. However, if your load fluctuates wildly, the cloud becomes a massive, unavoidable advantage. We see this all the time with interactive analytical queries.
Analyzing terabytes of data requires huge spikes of parallel computing power for a really short duration. In a self-hosted physical environment, you'd have to buy enough hardware for that absolute maximum peak load. That means your incredibly expensive servers just sit there completely idle, burning cash like 90% of the time. The cloud solves this beautifully. You can just rent thousands of processors for exactly 10 minutes, run your query, and instantly return those resources, stopping the billing clock right then and there.
Moving right along to our second section, cloud-native architecture, rebuilding for the cloud.
It's absolutely crucial to grasp that cloud native represents a fundamentally different engineering paradigm. It is not just taking your old legacy software, copying it over a network, and running it on a rented virtual machine inside someone else's data center. Actually, scratch that. It's more like a total teardown and rebuild. Traditional software was built with very specific assumptions. It expects a generic operating system, a local, permanent file system, and a highly stable network. Cloud-native architecture just shatters those assumptions. It's a layered architecture. Instead of just relying on an OS, it relies on lower-level, purpose-built cloud primitives, things like globally distributed object storage or managed message queues to build higher-level, highly resilient systems. By building from the ground up to assume the system lives in a dynamic cloud ecosystem, engineers unlock vastly better query performance, almost instantaneous recovery from catastrophic hardware failures, and the ability to seamlessly scale and process exponentially larger datasets on the exact same underlying hardware. It's a real game changer. Now, to really visualize this shift, we need to clearly contrast traditional, self-hosted database systems with their modern cloud-native counterparts. Let's break this into two main buckets. First, we have operational systems, or OLTP, which stands for Online Transaction Processing. Think of this as the fast-paced, day-to-day heavy lifting of an app, recording a user login, updating a shopping cart, stuff like that. The self-hosted mainstays here are relational databases like MySQL and Postgres, but their cloud-native equivalents are vastly different beasts like AWS Aurora or Google Cloud Spanner, which actually distribute transactions globally. On the flip side, we have analytical systems, or OLAP, Online Analytical Processing. This is your massive historical data crunching, asking complex questions across billions of rows to spot business trends. Traditional systems like Teradata or ClickHouse are entirely distinct from their cloud-native titans, like Snowflake or Google BigQuery. These modern analytical engines are fundamentally engineered from day one to leverage the near-infinite, scalable resources of the cloud environment they live in.
Okay, section 3, separating storage and compute, which is also known as disaggregation.
We now arrive at what is arguably the most massive structural shift in all of cloud-native design, the disaggregation of storage and compute. To really appreciate this, you have to look at how computing worked for decades. In traditional computing, the storage, your hard drives, and the compute, your CPU and RAM, happened inside the exact same physical metal box. We relied heavily on local disks. And because spinning metal drives physically fail all the time, we protected our data using hardware RAID arrays, duplicating data across multiple local drives so that if one died, the system survived. Well, cloud-native computing completely separates the two. Compute and storage are now entirely disconnected entities communicating over a high-speed network. If a cloud virtual machine happens to have a local disk, the system treats it just like an ephemeral cache, a temporary scratchpad. Engineers literally design these systems knowing that the VM and its local disk could be terminated by the cloud provider at any second. Instead, for absolute durable truth, cloud-native systems write their data to massive, highly replicated, entirely separate object storage services, like Amazon S3.
And because of this fundamental split between storage and compute, cloud-native systems are almost always multi-tenant. What does that mean? Multi-tenancy means that the computation and data from dozens or even hundreds of completely separate organizations are running simultaneously on the exact same shared physical hardware managed by a single cloud service. This is exactly how cloud providers achieve incredibly high hardware utilization and keep costs relatively low. But make no mistake, it is a seriously difficult engineering challenge. Why? Because of the noisy neighbor effect. If you and another company are sharing the same hardware and their engineering team suddenly fires off a massively unoptimized, resource-hogging query, it could theoretically starve the processor and slow down your application. Modern cloud-native systems require intense, brilliant engineering behind the scenes to ensure strict resource allocation and absolute security isolation, guaranteeing that one noisy neighbor cannot degrade the performance or access the data of anyone else sharing that machine.
Next up, Section 4, Operations in the Cloud Era, the Human Shift. As the fundamental architecture has completely transformed, the humans required to operate it have had to evolve just as radically. We can trace a very clear evolutionary timeline here. Decades ago, we lived in the era of traditional database administrators, or DBAs. This was a highly stressful, manual existence. It meant physically racking servers at 2 a.m., manually monitoring hard drive space, and painstakingly applying OS patches to individual machines one by one. Then we entered the virtualization era, which abstracted away the physical hardware, but still required engineers to manually manage virtual machines and begin dealing with metered billing. Today, we have fully arrived at the DevOps and Site Reliability Engineering, or SRE philosophy. Now, the high-level goal of keeping the business online hasn't changed at all, but the methods are completely unrecognizable. A modern SRE rarely logs into a server manually. Instead, they write complex code to automate infrastructure using ephemeral, temporary services that spin up and down dynamically based on traffic. They built systems that expect hardware to fail and gracefully recover without any human intervention.
There's a quote that perfectly nails this mindset shift. Capacity planning becomes financial planning, and performance optimization becomes cost optimization. Just think about that for a second. When you move to the cloud, you're moving to a model of metered billing paired with virtually unlimited automated storage and compute power. In the old days, a bad piece of code might cause a physical server to run out of memory and crash the application. It was an outage, sure, but the cost was fixed. In the cloud era, if you write an incredibly inefficient query that accidentally spins up 1,000 parallel processors, the cloud provider will happily execute it for you. Your application won't crash, but you will experience the sheer, unadulterated terror of opening an astronomical, totally unexpected AWS bill at the end of the month. So your capacity planning is no longer about predicting physical hard drive purchases, it is entirely about financial forecasting. And making your database queries run faster isn't just about speed anymore, it's directly, aggressively tied to stopping your software from bankrupting the company. So, with the cloud handling the physical metal, does that mean operations teams are obsolete? Absolutely not. No way. The burden has simply mutated. Your operations team is now tasked with navigating a dizzying, massive menu of overlapping vendor tools and figuring out the exact right service for the specific job. They operate as high-level service orchestrators, taking incredibly diverse services from different vendors and gluing them together over networks, often without standardized APIs to help them out. They have to implement and enforce strict security policies across scattered systems. They have to meticulously monitor vendor resource quotas to ensure your application doesn't unexpectedly hit a hard limit and crash during a traffic spike. And as we touched on earlier, they spend a massive amount of their time doing digital detective work, painstakingly tracking down invisible performance degradations hidden deeply inside completely opaque vendor systems that they literally do not control.
Which brings us to our final section, making your choice. No one size fits all.
As we bring all of these concepts together, the most vital takeaway is recognizing that neither the cloud nor self-hosting is universally objectively superior. The right choice is entirely dependent on your organizational context, your specific workload, and your team's expertise. Ultimately, what we've uncovered in this explainer is that attempting a simple lift and shift migration, taking your legacy architecture and just renting a virtual machine to run it, is almost always a recipe for disaster. If you treat the cloud simply as someone else's data center, you will inevitably overpay and severely underperform. Successfully adopting the cloud requires a complete reimagining of your technical architecture. It demands embracing the radical separation of compute from storage, and it requires a massive, occasionally painful cultural shift within your engineering team, migrating away from manual hardware management and moving toward financial optimization and complex service orchestration.
I want to leave you with this final, somewhat provocative thought to help you evaluate your own systems. Are you truly building cloud-native systems, or are you just running legacy, self-hosted architecture on someone else's computers? Look critically at your infrastructure right now. Are you actually leveraging disaggregated storage, on-demand elasticity, and modern reliability practices, or are you simply paying a massive premium to hold on to the past? Answering that question honestly is the only way to unlock the true, transformative value of your data. Thanks for joining me on this explainer.